So let's take a look through some word problems, specifically focusing on half-life and doubling time for these kind of solving with logarithms and using exponential models. So as a reminder, I think what's going to be most helpful in this section is kind of a reminder of our exponential models. So having y equals and then initial value and then some growth or decay with some exponent that often represents time. Then we'll also look at one that deals with financial math, and we'll get a little review of that one. But there's our go-to exponential. Remember with b, that's going to be calculated with either 1 plus or minus this value r, which is the growth rate or decay rate. If it's growth, we add it on. If it's decay, we take it away. And then what we're also going to look at, so with half-life, there's also a formula specific to half-life. So how this goes is it is y equals and then a, so we still have some initial value. But then for this growth or decay factor, what we're going to use is 1/2 or like 0.5, because that would represent half being taken away. And then for the exponent, we use this x over h, where x is the amount of time that has passed. In fact, let me write that. X is the total time. And h is the half-life time. So half-life is the amount of time it takes to reach half of our original amount. So if we started with 100 grams of something, it's how long it takes to decay to 50 grams. So it's how long it takes to end up with half of what we started with. And as you imagine, doubling time would be if we are doubling it. How long does it take to double it? Which for this one, it has its own formula too of y equals a times, and then for our growth factor to double, we would use a value of 2. And then for the exponent, we'll have x over, and I used h up above. Let's use d here, where d represents the double time, how long it takes to double. So these two equations here, they link to our exponential models. They're just a little different with that exponent because it's a specific amount of time where we're seeing doubling or it becoming half. Those two equations are most useful when they tell you what the half-life or double time is. So we'll kind of switch between just our standard exponential model, but then I'll be sure to emphasize why we grab these for when it's helpful to plug them into there. Okay, so this first example here, so we have bismuth 210 is an isotope that decays, and I'm just going to highlight, so it's decaying by about 13% each day. What is the half-life of bismuth 210? So we want to know how long does it take to end up with 1/2 of what we started with. So with this one, because we're looking for half-life, I'm not going to use this function up above here that I just described for half-life. Again, this will be helpful when we know what the half-life is. Instead, I'm going to use that function, just y equals a times b to the power of x. Now, in terms of what we know here, they don't tell us an amount that we have, so we're going to save that for a little bit. In terms of our growth, or in this case, decay factor, so for b is going to come from taking 1, and then because it's decaying, we're going to subtract that 0.13, so that's a 0.87. So we could plug that in. We have this y equals a times 0.87 to a power of x, where x represents the number of days. And now we just need some more information. In fact, x is going to be what we solve for. So let's say we're starting with an initial value of a, and y is calculating the amount that we have at the end of this time period. So if we want half of what we started with, then what we could do is substitute in for y. We could plug in 1/2 of a. So if I take 1/2 of a equals a times 0.87 to the power of x, that sets up my formula to be calculating x as the half-life. So how long does it take to have our initial amount go to half of that amount if we have this decay rate of 13%? All right, and I'm just going to switch 1/2 to 0.5. It doesn't really matter which one you use. So what I can do is divide both sides by a. So I'll get a to cancel out completely, which is perfect because then we just have one variable. So 1/2 is equal to 0.87 to the power of x, and I'm in a situation where I need to solve for an exponent. And as soon as I say that to myself, I'm getting little flags saying logarithms. Logarithms are what we need when we want to solve for an exponent. So what we have here is a value of 0.5, base of 0.87, exponent of x. So switching to logarithm form, we'd have that exponent of x is equal to a logarithm base 0.87 of that value of 0.5, or a half. And then we go to the calculator. Now I'll need to use the change of base formula here, but it's not too bad. So I'm going to take natural log of 0.5 divided by natural log of that base of 0.87, and we get a 4.9773. And I'm just going to round that since there's some rounding in here. Let's see, they say it's about 13% each day. I'm just going to round that to 5 days. So the half-life of bismuth 10 is about 5 days. All right, so there's our first one. So just plugging in to our exponential model using that decay rate. And then since it's half-life, we're taking 1/2 of the initial amount as our output value and solving from there. Okay, carbon-14 is a radioactive isotope that is present in organic materials and is commonly used for dating historical artifacts. Carbon-14 has a half-life of 5,730 years. Let's go ahead and highlight that. So we have this half-life, 5,730 years, and we found a bone fragment, and it contains 20% of its original carbon-14 matter. We want to know how old is the bone. So this is a case where they tell us the half-life. So that's giving me H equals 5,730. And then in terms of that 20% of its original amount, that's kind of giving us our output value. So basically, because they gave us the half-life, we're going to use that equation that I gave up above that is y equals a times, and then since it's half-life, we're going to have the base be 1/2. And then for the exponent, we're going to have x over h. So for h, we know that's 5,730, so I'm going to have x over 5,730. So this sets it up in terms of half-life, of knowing the half-life, and then that decay factor is going to be 0.5 to represent that half decayed. So then from there, so I have too many variables here. I have y, an a, an x, but this idea that we're left with 20% of the original amount. So if our original amount was a, and we're left with 20% of it, instead of using y, what I'm going to do is 20%, which is the same thing as 0.2 of that original amount of a. So 0.2 times a is equal to a times 0.5 to the x over 5,730. Divide both sides by a. So we get 0.2 is equal to 0.5 to the power of x over 5,730. And now we have just one variable, which is perfect. It's stuck in an exponent, which tells me we need logarithms. So I have this value of 0.2, base of 0.5, and this exponent that's an expression of x over 5,730. So switching to logarithm mode, exponent of x over 5,730 is equal to a logarithm with base 0.5 of that value of 0.2. And then just to finish it off, we want to get that 5,730 out of the denominator, so I'm going to multiply both sides by that value. So x is equal to, I'm going to need the calculator for my change of base formula. So we're going to have 5,730 times, let's see, logarithm of 0.2 divided by logarithm of 0.5. And that'll be 13,304.6478. 13, sorry, I changed the screen, 13, yeah, 30. And we can just round to a whole number of time. Let's go ahead and say it's about 13,305. So how old is the bone? The bone is about 13,305 years old. And this is truly how they carbon date a lot of artifacts and pieces of information, is they know the half-life of carbon-14 and it's present, like it says, it's present in organic materials. So then if they can just know how much they have of the original amount, they can figure out how old that artifact is. Pretty cool. All right, let's go to doubling time. So this first one, we're going to talk about investing money, and we have this 8% compounded quarterly, and we want to know how long will it take to double the money. So this is a compounding formula, so this is tying to our financial math, which if we grab that formula was A equals P times 1 plus R over N to a power of N times T. So R is coming from that 8%, so R is 0.08. Since this is compounding quarterly, N is going to be 4. And then the idea is that we want to see how long it takes for our money to double. So we have original principal, so that was our original investment, and we want to see how long does it take to get 2 times that principal. So plugging in for A, the amount we want to end up with is 2 times the principal equals P, the principal, times 1 plus 0.08 over 4. And then in the exponent, 4 times, and then the unknown amount of time that we actually want to solve for, T. All right, if we divide both sides by P, we'll just have 2 equals. I'm going to simplify, I'm going to simplify it in there because it's not too bad. Basically, this 1 plus 0.08 over 4, I'd want to be careful rounding anything in there, so I'd want to keep that accurate as much as possible. In this case, it's not too bad. It rounds exactly to 1.02. But if I had more decimals, I would probably keep it all expanded out. And then that's raised to an exponent of 4t. My variable is stuck in the exponent, so to solve for it, I'm going to need logarithms. So exponent of 4t is equal to a logarithm base 1.02 of that value of 2. And then to get t all alone on both sides, I would just need to divide by 4. Or you could think of it as multiplying by 1/4 if that's easier. Either way, we're taking 1/4 times logarithm base 1.02 of 2. And then we'll go to our calculator. So I'm going to go 1/4 times, and then this will be log of 2 divided by log of 1.02 for that base, and that is 8.75. And let's see, how long will it take your money to double? We can go ahead and round that to a whole number, or let's keep the decimal. We'll still throw in the word about because it is rounded. So it will take about 8.75 this will be in years. How I know that is because when we said compounded quarterly, n equals 4 is the idea of how many times in a single year, so that kind of set our units of time. For the money to double. All right. Okay. One more example here. So we have a social networking website and it's growing exponentially. We have a doubling time here. So they're saying it's doubling every 5 months. So in terms of that exponential function I showed you up above with a doubling time, this is a case where that doubling time d is given to us. So d equals 5 months. If this site currently has 120,000 users, so it's kind of like our initial amount, and this trend continues, how many users will the site have in 1 year? So we're letting 1 year pass. So that's going to be our x is the total amount of time that's passed. Notice that the doubling time is in months. So I don't want to just plug in x equals 1. I'm going to plug in x equals 12 to keep the units in terms of months. So I have a little conversion there to make sure the units of time are matching up. All right, so with this one, we're going to have y equals our initial amount of 120,000. The base for the exponent is going to be 2 since we're doubling. And then we're going to have x divided by d, which would be 12 divided by 5. So we're going to plug that into our calculator. So I'll show you how to plug in a fraction for that exponent there. So 120,000 times 2 raised to the power of 12. If I type in divided by 5, okay, that's all good. Sometimes if you're typing too much into the exponent, Desmos will kind of jump down. So if you need to, you can use parentheses in the exponent. This turned out to be totally fine, but I always like to caution with that of if you can't get everything into the exponent, like it's not letting you type in, you can use parentheses in that exponent to group it all together. So I'm going to go ahead and round this to a whole number. So 633,364. And that would be about the number of users after 1 year.